Okay, in this tutorial, we'll be going over IMFs, and it's more of a review of stuff that we've done earlier in the year. So, if you remember, the total IMFs are the London dispersion forces that the molecule can do, and the types of polarity that it can do. And if you recall, from London dispersion forces, uh, these were dependent on the number of electrons that the molecule has, and we developed a range kind of just by trial and error. So we said that if a molecule has between 0 and 30, that the London dispersion forces were considered weak, and if it was between 30 and 70, we decided that the LDS were in the medium range. And then if it had more than 70, we considered the LDFs to be strong. And just to be sure, an LDF is, let's say this is your molecule, okay, and you have two molecules. Now, the electrons on the molecule, okay, are spinning around, okay, the molecule. Okay, in some points in time, all the electrons are arranged up here. And what it does is it exposes the proton middle. So there's kind of like a proton side and an electron side on the molecule. And then what it does is, since these positives are now exposed, what it can do is actually, or or you could actually, you could explain it this way as well. So you could say the electrons are now down here, okay, on this side of the molecule, and there's a positive side of the molecule here. So it kind of like makes these, it polarizes the molecule just by the fact that the electrons move. And what it does in a neighboring molecule is if the electrons are whizzing around here as well, then the electrons actually get pushed down here because of repulsion. So these electrons on the neighboring molecule get pressed down on this side of the molecule. So it induces a dipole just by the electrons not liking each other. And so what does that do is it exposes the proton half on this molecule. And so right here, so right here a um, you get an attractive force, and they say it's a instantaneous momentary attractive force right there. So you get these little, I'm drawing these little green dots here to show an attractive force. So that's a London dispersion force. Okay, in kind of like a crash course on LDFs. All right, so good quick way that you need to know. You need to understand how a London dispersion force works. So this is why we say the electron cloud, we could say it becomes more polarizable when you have more electrons. Okay, so we say the electron cloud is more polarizable. Okay, and the AP exam, they like the words, words like that. So you need to know how it works. We can't just say more electrons, so more LDS. You can't just like, think of it in a vacuum like that, because you will be asked to explain, or they might have some problem where they have the explanation of it. So you kind of have to know how it works. But with that said, we're just gonna, for the rest of this slide, this and the next slide, we're pretty much just gonna look at electrons. Okay, but realize this is what we're referring to when we say LDF, because hopefully you have this microscopic picture in your mind how when we say LDF that you know what it means, a polarizable electron cloud. All right, so for HCl we have chlorine, which is 17 plus 1, so that's 18 electrons. So that falls in a weak category. I think all these are going to end up being weak, but you're comparing them, so relative to one another, they may or may not be, relative to one another, may not be weak. This is more on an absolute scale, these here. Okay, so argon is 18 also. So argon is 18 electrons. And F2, oh, it looks like I made them all 18 on purpose here. So all our LDFs are relatively same. It's the same. However, this one thing to note here is this one's actually monatomic, which means it has a lower surface area. So HCl is diatomic, so you get that cloud effect, that instantaneous dipole effect is better on this molecule. And then we have F2. This is also diatomic. So these two are going to be HCl and F2 are going to be really similar because they're both linear. This one will be slightly less. So this one is less than the other two. Okay, and this one will say weak. Okay, and about equal to HCl. Okay, as far as polarity, so HCl. Okay, this is going to be polar. So this is going to do dipole dipole. Uh, AR is this is nonpolar. I mean, it's monatomic. It's not bonded to anything, so that's nonpolar. And then F to F, there's no dipole arrow to draw there, so this is also nonpolar. So ranking of IMF. So this has several things going for it. So for HCl, so we have the fact that it's diatomic, and it can do dipole dipole. So this will be number one. We'll say number one is best IMFs. Okay, and followed by fluorine would be number two, and then argon should be the worst. Okay, so it says which has the highest boiling point. So a conclusion that we can make here is that a high boiling point means, or let's say it the other way around. Let's say the more IMFs means the more uh, molecule to molecule attraction. So they're stuck to one another better. So it's going to take more. This would require more heat to phase change, which ultimately this is the whole reason we're going over these again, is because we're about to go into phase change, and the cornerstone of phase change are the IMFs, the intermolecular forces. Okay, so if you could explain those really well, heating curves, solving heat problems, solving enthalpy of phase change problems, understanding what the values for enthalpy of phase change are, all that stuff is super easy if you understand this chart here and you could explain it in terms of IMS. So the more IMS, the more molecule to molecule attraction, and it will require more heat to phase change it. Um, so which has the higher boiling point then? It would be HCl because it has the best IMS. Okay, and I hesitate again to say stuff like that. So HCl, why it has the best IMS? We need to do better than that. We need to explain everything that I wrote in red here. Okay, and again, if there's a common theme this year, it's to really try to picture the molecule to molecule interaction, to really think in terms of molecules and not just because when you just say HCl, it has better IMS. You're just saying words. Okay, we need to think in terms of pictures and molecule interactions here. Okay, so let's try this next example. Okay, H2O. So H2O has and remember we're counting total electrons. So the oxygen has 8, and then there's 2 more. So this only has 10 electrons. So this would be considered weak. The LDS. NaCl would be, let's see, this is an interesting one, 11 and 17. Okay, so it only has 28. Okay, so this says 28 electrons. Okay, so normally we would say weak if we looked at this in absolute sense. Okay, and then HF would be, let's see, fluorine is 9 plus 1, so this has 10 electrons, so this is also weak. Okay, so this one's weak, but more than the other two. Okay, so as far as polarity, so H2O, we know this does hydrogen bonding. And NaCl, okay, NaCl, let's think a little bit here. It says put H bonding, dipole, dipole, or nonpolar. Okay, this is better than H bonding or dipole, dipole. You know why? This is metal to non-metal, so this is ionic. Okay, and so things that are ionic, they have melting points and boiling points in the thousands of degrees. Okay, because they're ionic, so which is the best type of IMF possible. Okay, and sometimes it's just so obvious that I didn't. Sometimes I just fail to mention this actually. So it's an alternating pattern of ions here. So for NaCl, so it's a positive, a negative, a positive, a negative. So this thing is like a brick house. Okay, with like mortar. This is held together exceptionally well. Okay, so this is like um, I mean this type of structure is incredibly strong. So this takes thousands of degrees to get it to. So you're trying to make like salt, NaCl. You're trying to vaporize salt. So just think about how much heat you're gonna have to get this into gas form. Okay, so HF actually does hydrogen bonding. This one doesn't come up too often, but because all it can do is H to F. So the usually we're used to seeing hydrogen bonding with O to H or N to H, but this one also does hydrogen bonding. So ranking of IMFs, this is by far number one. Okay, number two would be um, let's see, let's see here. So number two, it should be water. Okay, because the reason is for HF, you could do one hydrogen bond per molecule, but then if you have water, okay, if you write water upside down like this, okay, you could see that water can do per molecule can actually do two effective hydrogen bonds. So that would be the reasoning there, and this would be third. So what has the lowest freezing point? Well, I like to think of freezing point in terms of I like to think of freezing point in terms of melting point. So freezing point and melting point happen at the same temperature, but they're just opposite in direction. So if you go solid to liquid to gas, okay, right here is the melting point. Okay, now if you go the other way, this right here would be the freezing point. It's just easier to wrap your brain around melting point because I always think of things in terms of heat being added. So the lowest melting point would have um, the would actually have the worst IMFs. So it should be HF. So lowest freezing point, um, meaning it requires it to be the coldest for it to solidify. So that's what this. So I'll put these parentheses around here. So it means to erase this here. So this means it needs the coldest temperature to solidify. Another way to think about it, solidify. Okay, and that would be the worst IMFs. So that would be HF. Okay, so I'm going to have this next slide and have you guys try this one to fill in this chart here. And I think we'll end our tutorial here. Next up, this is all kind of like leading up to phase changes and enthalpy of phase changes. So we'll stay tuned for those upcoming tutorials. Okay, so we'll end this one here. Good luck with this one.